All right, these are the answers to our review for our 9, 7, 9, 10 test. We were given a power series here for a function f of x, and then we were asked to find some values. So when you're given a power series, f of 1, since it's centered at 1, is always going to be the first number you see. So the f of the center will always be the first term. F prime of that will then be the coefficient in front of the first polynomial piece. So -9 would be that. Now when you go to the second derivative, however, you got to be a little careful, because for the second derivative, it's coefficient times x minus 1 squared over 2 factorial. So this the fact that 2 factorial is already sitting here means that our coefficient part would just be the 27. Now if that 2 had not been there, we'd have to create that. So for example, if say it had been 6x minus 1 squared, we would have to write that as, or at least see it as this, and then the coefficient would be the 12 then. Okay. So you got to be a little careful with that. Now it becomes more tricky when you say, what about the 403rd, right? So here's the deal. The 403rd derivative of f at 1 is going to be part of the 403rd degree term, which will look like this. 403rd derivative will be the coefficient. Here's the polynomial. Here's the factorial, right? So what I'm going to do is I'm going to go, well, what would that be here? So if I want that same degree, then I need n to be 403, right? So if I were to put 403 in here, what I would get is -1 to the 403. So that would be -1. 3 to the 404th power, x minus 1 to the 403, and then over 403 factorial. Okay? So in other words, this is how you would build it, and this is what it actually is based on the general term. So if I were to multiply by 403 factorial, if I were to divide by x minus 1 to the 403, my 403rd derivative would be a -3 to the 404th power. That's the coefficient. For number 2, now we have a function g of x. We're told some things about what's going on at 8. Can we create a third degree Taylor for this at 8? And that's not a problem. The third degree Taylor for this would be g of 8, which is 10, then plus the g prime, that's our coefficient, times x minus 8, because we're centered at 8. Then minus 5, there's our coefficient, x minus 8 to the second over 2 factorial. And then plus 2.4 x minus 8 to the third over 3 factorial. So that's not too bad. All right. Then it says, can you use this to approximate g of 8.4? So in other words, put 8.4 into this function and see what you get. So on a calculator, I'm just going to go ahead and go 10 plus 4 times 8.4 minus 8, that's 0.4. All right, minus 5 times 0.4 squared divided by 2. And then plus 2.4 times 0.4 to the third divided by 3 factorial, which is 6. All right, we end up with 11.2256. And since it's exactly 4 decimal places, I'll just give the whole thing. Okay. So now C says for n's greater than 4, the nth derivative of g is given by this formula. So what is the Lagrange error of this estimate? So in other words, we have used a third degree polynomial, right? So g of 8.4, which is something we have no idea. We have no idea what that value is. But the difference between that and the approximation that we use. So this is the actual value. This is the approximation. The difference between them would be less than or equal to the next term that we didn't use. Okay? So how would you build that next term? Well, that would be the 4th term, right? We're looking at the 4th term. We would use the 4th derivative, or at least the maximum of the fourth derivative. Now, if the derivative is given by this for all that, and then what we're going to do is we're going to put 4 in here. We're going to get 12 plus 5 is 17 over 4 squared, which is 16. We are told that that would be the fourth derivative no matter what x value you're at. Okay? Whereas these were told, you know, what was going on at 8 specifically. This is a kind of a unique situation where it doesn't matter what x is, the derivative will be that no matter what. Okay? So that's our maximum. All right, times x minus 8 to the fourth power, but we're using 8.4 as our reference point, right? So it's 8.4 minus 8 to the fourth power over 4 factorial. We're building that term using this as the way to get the multiplier, putting 8.4 in there. So with the calculator, we're going to go 17/16 times 0.4 to the fourth power divided by 4 factorial, which is 24, and we get 0.00113 repeating. I could try to change that to a fraction. Let's see if it, no, won't let me, but that's all right. This is what we end up with here. So we know that this approximation, 11.2256, is within this amount of the correct answer. That's what we're being told. All right, then we have a function sine x. We want to use the third degree polynomial for this function to approximate sine of 0.5 and show that it's within 1/3000th of the actual answer. Okay, so we should know what sine x is. Sine x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and so on, right? We should be able to do that just from memory. If you have to build it, you can, but that's just kind of time you don't need to spend. We want to use the third degree Maclaurin, so that means we're just using this right here. So our approximate, we're saying that the sine of 0.5 is approximately 0.5, put it in for x, minus 0.5 to the third over 3 factorial. All right, we're just using those three, okay? And if we do that on a calculator real quick, I get 0.5 minus 0.5 to the third divided by 6. I get 0.47916 repeating, okay? If I go as a fraction, it's actually equal to 23/48 as a fraction, okay? So that's our approximation. We're not saying sine is that, we're just saying that it's about that. So we want to show that it's within this 1/3000th. So the actual value of sine of 0.5, this is the actual value, I don't know what it is, minus the approximation we came up with, 23/48. Okay, the difference between that is going to be less than or equal to the next term that we chose not to use. Now, because it's an alternating series, I don't have to do Lagrange here, which is great, because Lagrange can be a little confusing. Whenever it's an alternating series you're using to approximate, we can just use the very next term, which is that x to the fifth 5, right? So I can go 0.5 to the fifth over 5 factorial, okay? I take the calculator and go 0.5 to the fifth divided by 125 factorial, and see if I can change that. All right, I do it on the calculator, change it to a fraction, it's 1 over 3,840. Okay, it's like 0.0002604. All right, we know that this approximation is less than or equal to this amount, and that is less than 1/3000th. So that proves that we're within 1/3000th of the right answer, because the error that we get from this is less than that. Part B says, can you use the Maclaurin for cosine to write the first 3 terms of this sine cosine? So we know again that sine is x minus x cubed over 3 plus x to the fifth over 5, and then so on. Cosine is 1 minus x squared over 2 plus x to the fourth over 4, and so on. So what they want us to do is to say, well, That's what g of x is. It's this infinite series times this infinite series. Obviously, that's a lot of terms. Can we come up with the first three terms? So if I go x times 1, I get x. X times this would be a negative x to the third over 2. X times that would be x to the fifth, x to the fifth over 4. All right, that's probably good. Let's do the next one. This will be negative x to the 3 times 1, so negative x to the 3 over 3. Then this would be a positive x to the fifth over 3 factorial, 2 factorial. And then a negative x to the 7 over 3 factorial, 4 factorial. Okay. Then go to the next one, x to the fifth, 5 factorial times 1. Now, if I'm looking for the first three terms, I see x, I see an x to the 3, I see an x to the 5. Probably don't need an x to the 7, so I can kind of stop there. I don't need to go up to x to the 7th or x to the 9th or anything like that. Okay. So g of x is equal to this, and then it keeps going and going and going. And so we're going to say that g of x is approximately x. Okay, then I've got negative x to the third over 2 factorial, so over 2, and then negative x to the third over 3 factorial, which is 6. So if I make this 3, 6, negative 3, 6 minus that would be negative 4, 6, or a negative 2/3 x to the 3. Okay. And then I've got a x to the fifth 4 factorial, that's 24. I've got 6 times 4, that's 24. And then I've got 5 factorial, which is 120. That's 24 times 5. So if I multiply these by 5, that gets them up to 120. So I've got 5 of them plus 5 of them plus 1 of them. That's 11 120ths x to the fifth. Right. And again, I don't need to worry so much about the x to the 7. I just wanted the first three terms. There's the first three terms. So you're distributing this, being real careful, and then when you get to here, just look for the first 3 degrees, and that's what they're looking for.